All right, so I'm going to start with the first two questions that you asked me. The first one is pretty straightforward. It's asking a solution of which of the following pairs will be a buffer solution. So a buffer solution is going to be something that resists pH changes. So it's kind of like if you're in an argument with someone and you want someone to buffer that argument, where you want them to kind of get in the middle and they kind of appease both sides and keep you from getting too extreme. So a buffer is going to resist moving to acidic if you add an acid, and it's going to resist moving to basic if you add a base, all within the range that it's capable of buffering, which is usually within plus or minus 1 pH unit of the pKa of the weak acid. Okay, so to have a buffer pair, what I'm looking for is a weak acid, which means something, an acid, we generically write acids HA. So I'm looking for an acid that when I put it into water is not going to completely dissociate into protons and conjugate base, but it's only going to partially dissociate as indicated by these two arrows, the one going forward and one going back, as opposed to a strong acid, which is going to also have the abbreviation HA, but it's going to 100% dissociate into H plus for protons and A minus. Okay, so again, this is a strong acid. It's going to dissociate 100%, and this is a weak acid. It's only going to dissociate a little bit. So with a weak acid, the only way to know the difference between weak acids and strong acids is that you have to memorize them. There's a very small list of strong acids. Most things are a weak acid. However, of course, on the list that they gave you, which includes hydrobromic acid, hydrofluoric acid, hydrochloric acid, and hydroiodic acid, 3 of those 4 options include a strong acid, and only one of them is actually a weak acid. Okay, so the goal to making a buffer solution is that I want a weak acid, one of these, and then I want a salt that contains, oops, salt has an L in it, a salt that contains this conjugate base of the weak acid. So for example, if I'm talking about, the example, I can't come up with acetic acid, right? So I'm just going to abbreviate it HAC for acetic acid. Acetic acid is going to dissociate into its proton and the acetate ion. If I wanted to make a buffer for this acetic acid, I need a salt that contains the acetate ion. So I would use this salt sodium acetate. Okay, so acetic acid and sodium acetate together would make a buffer solution. Why? Because I have a weak acid and I have a salt that contains the conjugate base of that weak acid. And basically what's going to happen when I put this in solution is that this is going to dissociate a little bit, very little, and this is going to dissociate completely. And we'll get to that, the implications of that in the next problem, which involves the Henderson-Hasselbalch equation. But to answer this question, all we need to know is we need to find the weak acid and the conjugate base that contains its, the salt that contains its conjugate base. And in this case, the only one that fits that profile is hydrofluoric acid, which is a weak acid, and cesium fluoride, which is a salt that contains fluoride, which is the conjugate base of hydrofluoric acid. For the next question, this one is going to require the Henderson-Hasselbalch equation. So this question gives us an acid and a salt, and they're both being added the same number of moles, and they're both being used to make up a solution that is a liter, if I'm not mistaken. So it says, calculate the pH of a solution prepared by dissolving 0.150 moles of benzoic acid and of sodium benzoate, so I assume that also means 0.125 moles. 0.150 moles of sodium benzoate in enough water to yield a 1 liter solution, and then they give us the Ka of benzoic acid. Okay, so for this one, this problem, I'm going to use the Henderson-Hasselbalch equation, which if you're not familiar with it, this is going to be really important whenever I'm dealing with acids and bases, especially with weak acids. And it's pH is equal to the pKa, which is a property of the acid, plus the log of the dissociated form of the acid, also known as the conjugate base, over the concentration of the undissociated form of the acid, usually abbreviated HA. So in this case with the benzoic acid, the HA is going to be equal to the concentration of benzoic acid that they give you, which in this case is 0.150 moles in 1.00 liters, which is equal to 0.150 molar, or moles per liter. So the reason why in this case I can treat the benzoic acid concentration as equal to the HA, even though in reality it's going to dissociate a little bit into A- and H+, is that the concentration of A- is really going to be dominated by the addition of the sodium benzoate. So because if we look at the pKa of the sodium benzoate, or sorry, the benzoic acid, they tell us that the pKa is equal to they give us the Ka, right? The Ka is equal to 6.3 times 10 to the negative 5 is the Ka. So that is very, very, very small, right? That's the dissociation constant for this acid. And what that means is that when I put it into solution, most of it is going to stay in the undissociated form, the HA, and the little tiny bit of it is going to dissociate to give off A-. However, compared to the amount of sodium benzoate which I'm adding, which is also, so A- in this case is sodium benzoate, which is equal to, so concentration of sodium benzoate, which is also in this problem equal to 0.150 moles in 1.00 liters, or 0.150 molar. This 0.150 molar is so much bigger than the Ka, and that means that I can pretty much assume that the concentration of A- that is contributed by the dissociation of the benzoic acid is negligible relative to the amount of benzoate that's coming from the sodium benzoate. Okay, so in case you forgot why I'm able to treat the sodium benzoate 100% as being my A-, it's because sodium benzoate is an ionic compound, and when I put ionic compounds into solution, they dissociate 100%. Okay, so now that I know my concentration of my A-, my concentration of my A-, the concentration of my HA, and I have my Ka, I can just plug it all into the Henderson-Hasselbalch equation. So the first thing I'm going to need to do is turn my Ka into a pKa, and anytime I see a little p in front of anything, I know that means to take the negative log of it. So pKa is just the negative log of 6.3 times 10 to the negative 5. So the pKa is going to be equal to the negative log of the Ka. So just save some room and write that there. And when I do that, I find that the pKa is equal to 4.2. Okay, and like I said, buffers are going to work most effectively within plus or minus 1 pH unit of their pKa. All right, so this is basically the pKa is the pH at which your solution is 50% A- and 50% HA. All right, so let's plug this into our Henderson-Hasselbalch equation. So again, we're trying to find the pH. So it's equal to the pKa, which in this case is 4.2, plus the log of the A-, which in this case is 0.150 molar, divided by the HA, which in this case is also, 0.150 molar. And when I plug that into my calculator, you'll notice that in this situation, I'm essentially taking, right, these are the same, so that's the log of 1, and the log of 1 is 0, so this term actually wipes out completely, leaving me with pH equals 4.2, or in this case, the pH equals the pKa. So this actually makes sense if we go back to the definition of what is pKa. So the pKa is the pH at which I'm going to have half of my acid dissociated, meaning in the A- state, and half of it undissociated in the HA state. And since in this case I added the exact same number of moles per liter of benzoic acid and sodium benzoate, it makes sense that my pH is going to equal my pKa.